You've seen them a million times, right? These tiny, perfect little jewels that just fall out of the sky. They land on your sleeve for a second, and then they're gone. But behind that fleeting beauty, there's an incredible story. It's a story of physics, of chaos, and of an epic journey that gets written, literally, into the structure of ice. Okay, let's get into it. So here it is. This is the one we all picture in our heads, right? The perfect six-sided star. It's so familiar, it's basically the logo for winter. But this everyday little thing holds some seriously deep secrets. I mean, how does plain old water, H2O, build itself into something with this much detail, this much symmetry? And all that mind-boggling complexity leads to that famous little piece of trivia we all learn as kids. You know the one, that no two snowflakes are ever exactly alike. But come on, is that really true? I mean, with trillions and trillions of them falling every single winter, all over the world, you'd think at some point two of them would have to be twins, right? Well, to figure that out, we have to look at what they're made of. And the scale of it is just staggering. Okay, that number, that's 10 quintillion. That is roughly how many water molecules make up one single average snowflake. 10 quintillion. With that many tiny little building blocks, and each one taking a slightly different tumble on its way down, the number of possible arrangements is just, it's astronomical. So vast that the chances of two ever being identical are, well, basically zero. So, okay, they're all unique. But the story gets way cooler because it turns out that classic star shape we all know and love, that's just one face in a massive crowd. Let's take a look at the absolute zoo of different snowflake types that scientists have found. I mean, just look at these two. On the left, you have a hollow column. It's simple, clean, almost like a tiny piece of architecture. And on the right, a fern-like stellar dendrite, which is one of the biggest and most complicated types there is. It's hard to believe they're both made of the exact same stuff, frozen water. And get this, even within the same family of shapes, the variety is just huge. Both of these are technically plates, but the one on the left is smooth, perfect, like a tiny jewel. The one on the right, though, has these bold ridges that cut it up like a pizza. Same basic idea, totally different personality. So naturally, scientists have been trying to catalog this whole menagerie for decades. Back in 1951, the official list was pretty short, just 7 types. But then, as people like Ukachiro and Akaya started looking closer, that number just exploded, first to 41, and now the most detailed chart has 80 different types. And you know what? Nature can probably still come up with more. So how on earth does all this variety happen? Well, believe it or not, every single one of these wildly different crystals starts with the exact same fundamental recipe. Let's break down how each one gets its start. Okay, so picture this. Way up in a cloud, you've got a tiny speck of dust or pollen. A supercooled water droplet latches on and freezes around it. That's the seed. Now here's the key. It doesn't grow by bumping into other water drops. Instead, it grows by grabbing water vapor molecules right out of the air. And because of the unique shape of water molecules, they can only snap together in a 6-sided pattern. So every single snowflake, no matter how wild it ends up, starts its life as a simple, tiny hexagonal prism. Right, so they all start as a simple hexagon. The crazy, complicated shape it ends up with isn't random at all. It's a diary. It's a frozen record of the crystal's entire journey as it fell and tumbled through the clouds. Every twist and turn gets etched right into its arms. And the secret code to reading that diary comes down to just 2 things: temperature and humidity. Temperature is what decides the basic style of the snowflake. Is it going to grow out flat like a plate or grow up and down like a column? Then humidity decides how fancy it gets. Low humidity means slow, simple growth. High humidity, that's when things get crazy and you get all those beautiful, intricate branches. And this right here, this is basically the Rosetta Stone for snowflakes. It's called the Nikaya diagram. And check out how wild this is. Just a few degrees of temperature changes, everything. Near freezing, you get thin plates. Drop the temp to -5°C, and poof, you get long, skinny needles. Drop it even further to -15, and you're back to plates and stars again, but now they're the biggest, most spectacular ones. It's this bizarre back and forth that makes each snowflake's journey so unique. And if you want the perfect proof, just look at this weirdo. This is a capped column, and it's a crystal that's literally telling you its life story. You can see it started its journey in a part of the cloud that was about -5 degrees, so it grew as a column. But then it must have fallen into a different temperature zone, maybe around -15, where plates like to grow. So what happened? It's sprouted two flat plates on either end. It's a frozen flight log. So the journey explains the shape. Mystery solved, right? Well, not so fast. Because for physicists, knowing that it happens is one thing, but knowing why it happens on a deep fundamental level, that has been a huge puzzle for a really long time. To really get the mystery, you gotta know that there are two forces at war here. First, there's a process called faceting. This is the stabilizing force. It's the natural tendency for a crystal to want to form smooth, flat surfaces. If faceting was the only thing going on, all snowflakes would just be simple, boring little hexagons. But faceting is constantly fighting against this other thing, branching instability. This is the chaotic force. The idea is that any little corner or point that sticks out farther into the moist air grows just a little bit faster. And that makes it stick out even more, so it grows even faster. It's a runaway feedback loop that creates all the beautiful, complex branches we see. So you have order versus chaos. That should explain it, right? Well, for decades, it didn't. Physicists couldn't create a model that explained the Nikaya diagram. They couldn't figure out why a tiny shift in temperature would cause this dramatic switch from columns to plates. Their models just didn't work. Something crucial was missing from the equation. And that missing piece, according to the latest theories, is a wild idea called knife edge instability. Basically, it suggests that the very tip of a growing thin branch of ice is molecularly messy. It's not a perfect, stable structure. And that messiness makes it incredibly good at grabbing new water molecules out of the air. So you get this other intense feedback loop. The thinner the edge, the faster it grows, which keeps the edge thin, which makes it grow faster still. This instability acts like an amplifier, turning tiny little changes in the environment into the huge differences in shape that had scientists stumped. And the proof is in these incredible computer models. Scientists call them snowflakes, which is perfect. And for the first time, using these new theories, they can actually simulate the growth of crystals that look just like the real thing. They can finally model that delicate dance between the forces of order and chaos. We are right on the verge of truly cracking the snowflake code. In the end, I think Yukichiro Nakia, the scientist who first mapped all their amazing shapes, really said it best. He called them letters sent from heaven. For centuries, they were letters written in a language we couldn't quite understand. But now, after all this time and all this science, we're finally learning how to read them. We're finally learning to understand the epic story that each and every one has to tell.